The next thing we're going to look at is the electric field due to a volume charge. So in order to do this, we're going to consider a sphere that is centered on the origin, as I've tried to draw here. We see that the sphere has some volume charge density rho sub v, and we're not going to go through the derivation of this, but if you want to see more details on that, you can look on pages 123 to 125 in the textbook. And ultimately what we're going to say is we want the electric field at some observation point P, which is outside of the sphere. So we're just going to say it can be shown, and again, you can look at that derivation in the textbook if you want to see some more details. But we can say that the electric field, and a key point here is that we're talking about outside of the sphere, and we'll come back later with Gauss's law and we'll sort of see what's going on inside, but outside the sphere, our electric field is given by E is equal to Q, so capital Q divided by 4 pi epsilon naught r squared in the r direction. So let me define a few of these things explicitly. So our Q is the total charge in the sphere, and of course we can get that by multiplying the volume by our charge density rho sub v. And so again, that's going to be our total charge in the sphere. All right, our r, we see the r squared in the denominator, is going to be the radial distance from the origin to the observation point. So in this case, let's just say P. So if we were to draw this out, of course, our r would look, don't want to erase, our r would look something like this, radial distance from our origin to point P. And then, of course, u sub r is just going to be the unit vector in that direction. So unit vector in the r direction. And so you might be asking yourself, well, this seems pretty limited because we have to have the sphere centered on the origin. Well, a couple things to note. Of course, one, we can define our origin wherever we want for a particular problem, particularly if we only have one charge structure that we're considering. And two, maybe we can't define the origin at the center of our charge structure, then this r and unit vector r just become locally defined, the same way we saw when we were talking about our infinite line. So it just becomes the radial distance from the center of the sphere as opposed to from the origin. And so something we can notice, looking at the form of this equation here, is that this looks the same as the form of E due to a point charge at the origin. So same form as E due to a point charge. And so our point charge would have to be capital Q, so it'd have to have the total charge that's contained in the volume. And if that point charge is at the origin, to be more general, we can say at the center of the sphere. And so what that tells us is that basically if we have a spherical volume charge, if we're looking at a point outside of it, then we can just treat it like a point charge located at the center of the sphere with a charge that's equal to the entire charge in the volume. And as I mentioned earlier, we're going to come back a little later on with Gauss's law, and we're going to figure out a way to get some expressions for what's going on inside the sphere as well.